Now next topic, that is electrostatics of conductors. So electrostatics of conductors, in that we have to understand certain fundamental things related to conductors. So first thing, inside a conductor electric field is zero. So how we can say inside the conductor electrostatic field is zero? Because inside the conductor there is no motion of electric charges in a particular one direction. If electrostatic field is there, then definitely the electric charges will experience the force, and under the effect of that force it will execute motion in a particular direction, and due to that the current will be constituted. But practically we never observe this thing, so we can say inside a conductor electrostatic field is zero. Second thing, at the surface of charged conductor electrostatic field must be perpendicular to the surface at every point. Now how we can say this electrostatic field is perpendicular to the surface? Because suppose at the surface of the conductor the electric field is not perpendicular to the surface. Suppose it is not perpendicular. Then what happens? If electrostatic field is at some other angle, then you will get two components of electrostatic field. One is perpendicular to the surface, another one is parallel to the surface. And if parallel to the surface electrostatic field is present, then the electric charges will experience the force due to this electric field, and it will constitute the current at the surface. But there is no current on the surface, so we can say when the charged conductor is there, then charges are stationary on that, and we can say that is only possible if the electric field is perpendicular at each and every point on the surface. Now the interior of the conductor can have no excess charge in the static situation. Here, if net charge of the conductor that is equal to zero, then and then only it is possible electrostatic field is zero. So in accordance to that we can say this thing, here there is no excess charge inside the conductor. Now electrostatic potential is constant throughout the volume of the conductor, which is equal to the value of the potential which is at the surface. And if inside the conductor electric field is zero, then we know this thing, electric field E, that is equal to minus dV by dr. So differentiation of electric potential with respect to the displacement, that is equal to zero, means electrostatic potential that is constant one. Now electric field at the surface of a charged conductor, its value. So how we can calculate it? Suppose here we consider a conductor which one is charged 1, and here the surface charge density, that is sigma. Now here consider a pillbox type infinitesimal small Gaussian surface. Partially it is inside the conductor, partially it is outside the conductor. Now at the surface electric field is perpendicular to the surface, we discussed it. Now here for this electric field component in this particular direction, that is zero, it implies that if we think about the surface which one is a cylindrical one, for this pillbox the flux associated with it, that will be equal to 0. or in other words we can say electric field, and here the area vector will be perpendicular to each other. So flux passing through it is 0. Now for this lower surface, it is inside the conductor. Inside the conductor there is no electric field. So flux passing through it, that is also 0. So here flux will pass only through this particular flat surface. Here electric field and the infinitesimal small area vector, both will be parallel to each other. So we can say flux passing through this Gaussian surface E dot delta S, that is as per Gauss's law, sigma q upon epsilon 0, where sigma q, that is the net charge enclosed by the surface. So here net charge that will be enclosed by this surface area which is at this surface. So we can say that is sigma into delta S, because sigma, that is surface charge density, that is charge per unit area. So we can write now E delta S, that is equal to E and delta S both are in the same direction. So E dot delta S, that is E delta S cos theta. Theta is 0, cos 0 1. So directly we can write E delta S, that is net charge enclosed sigma into delta S upon epsilon 0. Delta S cancelled. So at the surface, the electric field, that is E equal to sigma upon epsilon 0 magnitude wise, and in vector form we can write vector E, that is sigma upon epsilon 0 n caret, where n caret, that is the unit vector which is in the direction of electric field, or we can say perpendicular to the surface. Then electrostatic shielding. If we think about a conductor with cavity, if we have a conductor with cavity, then inside the conductor anywhere electric field is 0. Suppose this conductor is placed in external electric field, then negative charges will experience the force in the opposite direction of the field. Positive charges will experience the force in the direction of the field. And under the effect of it, the accumulation of charges will take place at the surface. And due to that, here the electric field will be developed. But this electric field developed will be such that the resultant electric field inside the conductor and inside the cavity, that will be 0. So here this particular fact, in any situation, if the charges are there on the conductor, if conductor is placed in the external field, but inside the cavity the electric field always remains 0. So this fact is known as electrostatic shielding, and this one is a very useful feature. If you want to protect any sensitive circuits, electronic circuits which are sensitive to electric field or change in electric fields, then if those circuits are shielded with the help of this concept, then any type of change in electric field on outside it, no disturbance will be there in the electronic circuit. Clear to all of you?